this is Niloufar Salehi, and today I'm happy to share our research titled Comparative Evaluation of Dissolution Performance in USB2 Setup and Alternative Stirrer and Vessel Design, a Systematic Computational Investigation. To start with, I want to give you an overview about in vivo hydrodynamics versus in vitro hydrodynamics. As you know, under in vivo hydrodynamics, in a stomach and a small intestine, the segmentation, contractions, and peristaltic movements are generating hydrodynamic conditions. However, under in vitro system, for example, in this case, USB2, a stirrer, in this case, paddle stirrer, is generating the hydrodynamic conditions. The computational fluid dynamic stimulation for a small intestine fluid pocket shows that the shear rate at its maximum reaches 5 reciprocal seconds. However, for USB2 apparatus operating under 50 RPM, the maximum shear rate can reach 100 reciprocal seconds. Therefore, there are inconsistencies between the in vivo and in vitro hydrodynamic condition, and there should be an effort to make them more comparable. But why hydrodynamic parameters are important for drug dissolution? If we focus on a well-mixed region of the fluid, particles are suspended in the fluid, and each particle is surrounded by an unstirred layer, which is called the boundary layer. Boundary layer differentiates between the particle surface and fluid bulk. The particle radius shrinkage rate or dissolution rate depends upon the thickness of this layer. The diffusion layer thickness depends upon the particle radius or particle size and Sherwood number. Sherwood number has different components of diffusion, confinement, shear component, which is as a function of shear Reynolds number and shear Peclet number, and both of them depend upon the shear rate. Also, the convective component, which is as a function of Reynolds slip number and Peclet slip number. Both of them depend upon delta U, which is the relative fluid velocity with respect to the particle velocity. Therefore, it is very important to understand the shear rate and fluid velocities under in vitro and in vivo system in order to understand the dissolution better. So the present challenges with the in vitro dissolution setups, one of them is coning. Coning means the accumulation of solid dosage form in the dead zone area of the USB2. Also, there is lack of homogeneous mixing and insufficient understanding of the shear rate and fluid velocities. In this work, we address the following. First of all, we introduce the alternative for vessel and a stirrer design to resolve the coning issue, and also we introduce new design that can improve the homogeneity of hydrodynamic condition. And finally, we present a comparative analysis of hydrodynamic parameters between current design and alternative designs. The design parameters that we looked in this study are using different stirrers such as hydrofoil, pitch blade, Rushden, and paddle stirrer. We also looked at different design parameters in a vessel such as the diameter of the tank, diameter of the impeller, the thickness of the impeller, the clearance, which is the distance from the bottom of the tank to the bottom of the stirrer. Also, we looked at different vessels. We compared the dished bottom vessel, which has a hemispherical region like USB2 vessel, with a flat bottom vessel. For computational fluid dynamic simulations, we use COMSOL multiphysics software. We solve for the Reynolds average Navier-Stokes equation in rotated frame with addition of Coriolis and centrifugal force. We solve for continuity equation and also the turbulent kinetic energy and dissipation rate of turbulent energy. In another word, we use K-epsilon turbulent model. Here we show the result. We computed the radial velocity in USB2 apparatus in a distance 0.5 centimeter distance from the bottom of the tank, which is representative of the coning area. Here you see the velocity as a function of distance from the center from this center point at different design that we have studied in this work. So first of all, the H4 design, which was a hydrofoil in a flat bottom vessel with diameter of 70 millimeter and the blade attachment angle to the impeller hub equal to 60 degrees, showed the better fluid velocities compared to USB2 and the system that had a similar volume compared to the USB2, but they used a flat bottom vessel. The worst system in terms of generating fluid velocity in the coning area were using hydrofoil or pitch blade when we had the attachment angle to the hub, to the impeller hub equal to 45 degrees. Also, comparing a hydrofoil setup with a 60 degrees attachment angle to the hub showed an improved performance compared to the similar setup with 45 degree the blade attachment angle to the impeller hub. Also, the USB2 apparatus compared to a Russian apparatus had similar performance. Comparing a hydrofoil with 4-blade, comparing a hydrofoil with the same design parameters but having 4-blade as opposed to the one that has 3-blade, the system that had 4-blade showed improved fluid velocities in the coning area. Also, we compared the USB2 with a flat bottom vessel, which had the same fluid volume, the same stirrer type, the same diameter for the stirrer, and the same clearance, distance, and rotational speed. We computed the fluid velocity and shear rate distribution. And as you see for the flat bottom system, which is P3 system, there is a more skewed function as opposed to USB2, because in a flat bottom vessel, you don't have this hemispherical region, you can generate more homogeneous mixing. Also, comparing a USB2 apparatus, with another design system which has hydrofoil as a stirrer, but the same vessel as USB2, we computed the streamline function for this system. And as you see, hydrofoil can facilitate the upward fluid movements better than USB2. Also, that is true when you use the hydrofoil in a flat bottom vessel as opposed to using paddle stirrer in a flat bottom vessel. We also computed the volume average shear rate and volume average fluid velocity for all the systems that we have studied in this work. As you see, USB2 apparatus is or design shows the highest volume average shear rate and volume average fluid velocities. Coming back to the point that I made in the first slide, we know that there are inconsistencies between in vivo and in vitro hydrodynamics. The studies such this, using computational fluid dynamic simulations and using systematic design, changing the design parameters systematically, can help us to find the optimal design. And applying that optimal design condition may help us to improve the IVIVC. So as a conclusion, hydrofoil stirrer minimizes the coning and hydrofoil enhances the fluid upward movement. Also, the flat bottom vessel provides more homogeneous mixing compared to the round bottom vessel. And finally, CFD analysis facilitates finding the optimal design. At the end, I want to thank everyone who contributed into this research and our funding agencies. Thank you, and I would be happy to take any questions.